Hello, everyone. Thank you for joining us today via Zoom. For the uninitiated, I'll say a few things about who we are and what we aim to do. So, I'm one of three organisers for the Australian Geometric PDE seminar. Essentially, what we do, we're a group of people who are quite enthusiastic about giving people the opportunity to speak on topics in differential geometry, with a particular focus on those in the Australian region. We're mostly focused on giving PhD students and early career researchers the opportunity to speak on topics. Sometimes we make this a reading course, so we'll pick a topic that people like that have many textbooks and papers written on them, and we'll go through that. This year, however, we've decided to make this more focused on the individual research that our participants have been completing. So this year we're asking for contributions from HDR students as well as postdocs, and giving them an opportunity to talk about the great research they've been doing. So our first talk of this particular year will be given to us by Patrick. He's a Master's by Research student at the University of New South Wales. We're quite pleased he was able to speak at such short notice. So this is an introduction to Patrick. His topic that he's going to talk to us about now is cohomogeneity 1 gradient Ricci solitons. Thank you for this, Patrick.
Okay, so yeah, the first thing I want to say is
sorry. I thought you were muted, but you're not.
no. Okay, perfect. The first thing I want to say is there I did give a similar talk to this at Matrix. Hopefully there's sufficiently new stuff that's still interesting. But overall, talking about gradient Ricci solitons in dimension 4, and cohomogeneity 1 here is just a symmetry assumption we're using to essentially try and construct new examples. In dimension 4, this has been very successful. In particular, we can find some new expanders here, but when we start looking at the shrinking case, in particular, the compact shrinking case, we're running out of examples, and cohomogeneity 1, this symmetry assumption, has kind of run its course. Okay, so let's start motivating these things. If you didn't know what they are, that's okay. We'll talk about that now. So first of all, Ricci flow. These things are important in Ricci flow. Well, let's see why. First of all, if you haven't heard of Ricci flow, that's all right. It's a geometric PDE. We start with some initial metric and we evolve the metric opposite to its Ricci curvature. So of course, here's your obligatory Wikipedia photo on the right. Sorry. Okay, Ricci flow is the primary technique used in the proof of many notable theorems. Particularly, we have, of course, the Poincare conjecture by the work of Perlman and many other great mathematicians. We also have many other theorems like the resolution to the differential sphere conjecture, the Bohm-Wilking-Rounding theorem, and many others. Too many to name, but the point is Ricci flow is this very powerful technique that we want to use as much as we can. Okay, so let's start with some simple solutions, understand what Ricci flow is. The most simple solution is to say, okay, suppose I have constant Ricci curvature. In this case, I have what I call an Einstein manifold. So this is just a manifold with constant Ricci curvature. In this case, then the Ricci flow equation just becomes a super simple ODE. We can solve it and see that solutions are just explicitly rescaling the metric. In particular, if my Ricci curvature is positive, I have a picture that looks like on the right here. I start with my metric and I evolve it until eventually its curvature kind of blows up. It becomes really small and it vanishes at some time. Now, what happens if instead I have negative Ricci curvature? Then it exists for all time and it expands. If I have zero Ricci curvature, it stays constant. In dimensions 3 or less, we know what the Einstein manifolds are. These are the model spaces with quotients, but it gets a little bit more interesting in dimension 4. In particular, today we can actually find some new examples of these things in dimension 4. An example of one in dimension 4 that is in a model space that's shrinking would be, or that has positive Ricci curvature, is the Fubini-Studi metric. There's plenty of K3 Ricci flat surfaces, and we find the ones with negative Ricci curvature. Okay, in dimension 2, the only thing that kind of does this with Ricci flow is the shrinking sphere. In particular, first of all, let's talk about general solutions. Okay, if I have a compact smooth Riemannian manifold, okay, I can do this procedure. I can do Ricci flow until I hit a maximal time. If I do hit a maximal time, not infinity, then what happens to my curvature is it actually blows up. The only constraint that tells me I can't do Ricci flow is when I have a curvature blow-up. So wanting to do Ricci flow, the question is, how can we get around this problem? You know, I might want to do Ricci flow past some time. I might not have extracted all the, the geometric information or topological, and I have this obstruction. How do I get around that? How do I keep going? So like what I was saying, in 2 dimensions, the only case where this can happen is where something looks very, very similar to a shrinking round sphere. So what can we do? Well, let's just rescale. Rescale to make the volume constant. Now I'm doing the normalized Ricci flow. So I add this additional term to ensure that the volume stays the same. Well, great. Now I have no problems, and I get a unique solution to the normalized Ricci flow, starting at some initial condition on a compact 2 manifold, and I can just evolve that for any time. Okay, perfect. Now I have my Ricci flow. This is the tool I can use to prove, for example, the uniformization theorem. Okay, this is well known before Ricci flow even existed, but it is a tool you can use the powerful 2-dimensional theorem. And in particular, going to 3 dimensions, we get something new. But first, we need to build some more machinery. Okay, and these are Ricci solitons. So these are, kind of what we want to model, what the shrinking 2-sphere did in dimensions 3 and above. Okay, so the Ricci flow admits other homothetically expanding, shrinking, or steady solutions. These are exactly the Ricci solitons. So suppose I have a solution to Ricci flow. I have symmetric, and it evolves simply by rescaling and the pullback of some diffeomorphism that changes smoothly in time, starts as the identity. Okay, if I differentiate this equation in time, at time is 0, I get this equation with my Ricci curvature and negative, and this equation on my right with a Lie derivative. Okay, if I instead, specify a little bit more and say that this vector field is the gradient of some smooth function u, well, then the Ricci soliton just becomes this thing at the bottom here. In particular, that's enough. As long as my metric satisfies this equation, it will evolve just like this. So now I'm just going to say a Ricci soliton rather than a solution to Ricci flow is just this G0 metric itself. In particular, if my u is some constant, we do see that our Einstein manifolds reappear. I just have constant Ricci curvature. Now, what are examples of these things? Okay, of course, if I have my u constant, I just get my Einstein manifolds back. But what are some examples where u is not constant? Well, the most obvious example is the Gaussian soliton. I start with flat Rn, and I can add my soliton potential as this function, and now I can actually get any lambda. In particular, I can be shrinking, steady, or expanding. Great. Well, now if I have, some Einstein manifold or some different solution, I can do a Riemannian-Debret product, add the soliton potentials, and I get another thing. The one that's going to be important to us is, of course, when I have the sphere and I give it this Euclidean factor, and now it's shrinking, and it's a shrinking cylinder. Okay, the first example, which we'll call non-trivial, so it doesn't have this Euclidean Gaussian soliton factor or in an Einstein factor, is Hamilton's cigar soliton. So this is a steady Ricci soliton. It's this image I've given below. This is an image of Hamilton's cigar soliton. And if we think of embedding this in R3, it translates in the direction of its tail. So you can see that geometrically, it's not just shrinking or steady, or somehow more than that, but geometrically, it's actually saying the same. It's just translating. There's nothing really changing with it. So we should consider these as the fixed points of the Ricci flow. There's also higher dimensional analogs of this Hamilton cigar soliton, which we call Bryan soliton. And we'll see a picture of that in dimension 3 here. So that's the one just here. Okay, so dimension 3. Can we just rescale? The answer is no. So a good reason why that is, we can see with this rotationally symmetric dumbbell. So what I have here is the 3-sphere, and it's rotationally symmetric, so invariant under SO3, and I have 3 orbits that are 2 spheres of radius R1, R2, and R3. If these radii are all comparable, we get the case on the left. I evolve with Ricci flow, and I get something very similar to what I would expect in 2D. It goes to a point and looks a lot like a 3-sphere if I somehow zoom in correctly. However, if this middle radii is quite small in comparison to the other 2, well then the intrinsic curvature of the 2-sphere is sufficient that it actually has a curvature blow up before the rest of the manifold can. It vanishes before everything else can. I can't just rescale and get rid of this. I still have a neck, no matter what I do. So if I want to actually continue the flow and continue to get information by doing the flow, I need to resolve that without just rescaling. I need to do something more. We can also get, so those are the two generic cases. I can also get some kind of boundary case where these R1, R2, and R3 are chosen very specifically, such that, I actually get a blow up of curvature at a point, and if I zoom in correctly, this looks like the Bryan soliton. Okay, so what are these zoomed in things? So they're called singularity models. And how do we know what they are? Well, the first thing we know is that Ricci flow is invariant under parabolic rescaling. If I have a solution to Ricci flow, I can just rescale parabolically, i.e. like this, and now I have another solution and it exists for longer time for this alpha. In particular, if I choose points and times going to the point and time where I get a blow up of curvature and rescale these things appropriately, I can converge in some pointwise sense that we don't need to worry too much about to a solution that exists for all negative time. We call these ancient solutions, and these ancient solutions to Ricci flow is the correct way to zoom in to what's happening. And understanding what happens to these things, or really what they are, allows us to understand what kind of singularities we can form. Note that if the singularity model is of type 1, or if the singularity is of type 1, so the curvature blows up like 1 on T, then I get necessarily complete gradient shrinking Ricci solitons as my singularity models. Okay, so let's focus on that case. I mean, in dimension 3, we can actually say a lot more because these things have been studied a lot. So in dimension 3, we can say, singularity models are actually ancient kappa solutions, whatever that means, that doesn't matter. Okay, this shouldn't say non-compact. This is all the three-dimensional ancient kappa solutions are known thanks to the great work of Brendel and his co-authors in his second paper. We know that these things are exactly the round shrinking cylinder, the Bryan soliton, the round shrinking sphere, Perlman's ancient kappa solution, or some quotient of these things. So we've actually got quite a small list, and understanding what these things are allow us to kind of remove them and continue the flow. So we can kind of see this again. Evolving on the left, well, if I remove something, I remove everything. Perfect, I understand what's going on. But if I have this case on the right, what I want to do is kind of remove this neck. So do surgery. Now I have two balls and I can keep going the flow. In particular, this surgery allows us to keep doing the flow while changing the topology, but we understand what happens to the topology, and we can keep doing Ricci flow and extract information because we know what happens at the end, work backwards, and that's how Perlman found the Poincare conjecture. So again, a very powerful tool in dimension 3. The question is, can we keep doing this? Can I do this in dimension 4 now? So let's just start with a simple case. What are the gradient shrinking Ricci solitons in dimension 4? Okay, of course we have the Einstein manifolds. Great. And then we have products. So we have things from lower dimensions that combine together to give me other things. These are, there's not a big list for shrinkers. There's only 5 of them. And these are exactly the homogeneous gradient shrinkers. We'll talk about that a little bit later. And then there's just only a very small amount of other examples. So there's this Kähler cohomogeneity 1 compact example. There's a Kähler cohomogeneity 1 non-compact example. There's a Kähler toric compact example and a Kähler toric non-compact example. Okay, so obviously to find these things is either quite hard and we need a lot of symmetry, or there's not a lot of these things out there. So 2 things to note here. First of all, Kähler makes it a lot easier to find these things. It reduces that PDE, the Ricci soliton PDE, a lot, so we can understand what's going on. And particular Ricci flow preserves the Kähler class, so that does make sense. The other thing is, well, Ricci flow preserves symmetries, and also Ricci flow is some kind of smoothing PDE, so we should expect there to be quite a lot of symmetries in low dimensions. So it does make sense that, to apply some symmetries. Now, cohomogeneity 1, these aren't done, but Kähler, this is done. So all the Kähler shrinkers are known. So the next obvious step we should do is look for cohomogeneity 1 guys. In particular, let's have a group action, ensure that a metric is invariant under that thing. That'll make the Ricci soliton more tractable. Can we find anything new? So let's start with highly symmetric Ricci solitons. So I talked about homogeneous ones. Why don't we care about them? So the point is here that, okay, there's some great work done by Peterson and Weil. that all homogeneous gradient Ricci solitons are either really obvious or have a lower dimensional example and a flat Euclidean factor. So there's only 5 of these guys. And in particular, a nice way we can see that is if the action is by a compact group, then the soliton potential can be made invariant. In particular, for the homogeneous case, that means the soliton potential should, most of the time just be constant. And that's why we see these things have these Einstein metrics mostly. Okay, the next step, like we saw, these are cohomogeneity 1 metrics. We're going to focus on the case where the action is by a compact group. This means I can make my soliton potential invariant. This is an averaging procedure. And then after that, well, now my soliton potential is invariant. The Ricci curvature is invariant. The metric's invariant. Now everything is invariant within that, Ricci soliton PDE. So now it's just an ODE on the orbit space because the orbit space is one-dimensional. Great. So, like Kayla reduced us down, so does symmetry. Now I've got hopefully a much more tractable PDE, now an ODE, that I can solve. So what is this ODE? Well, the first question is not that, but instead, well, if I want to classify these things, what are the actions? And the question is, well, are there any more of them? So the question first is, if I have a compact, simply connected 4-dimensional Ricci soliton, if it's cohomogeneity 1, what can it be? So I have the Coiso-Sau metric we said before. I have some Einstein metric on the same space called the paid metric. And then I have, 3 really obvious examples. So the Fabini-Studi metric, the round metric, or the direct product of round metrics. Are there any more? And, we conjecture that there's probably not any more. And we'll see some numerical evidence for that. Okay, so, well, I want to classify these things. First, we need to classify the actions to then study the geometry of what the invariant things under these actions are. And the great thing is by some work, we can actually understand exactly what these actions are. There are, first of all, 2 actions by SO3, SO2. These are well studied. These are warped product metrics, and they've been very well studied. So we're going to leave them alone for now and focus on the case where we have a smaller group working, and that's SU2, or its quotient SO3, of course. So we have 4 actions, 2 and 3 here, and then I've got an infinite family of actions, which I split up into these last 4. So I have those 4, and I have 1 on the blow up at one point of CP2, and then 2 more on the on S2, S2. This infinite family continues with U2 actions, but again, U2 is kind of more invariant, and we're going to focus on the SU2 invariant ones, but we can actually say some stuff about these U2 invariant guys. But in particular, that leaves us with 7 minimal actions that we should consider. And they're the ones we're mostly going to be considering for the rest of this half of the talk at least. Okay, well, I have an SU2 invariant Ricci soliton. What do these things actually look like? So when we started with the Ricci soliton equation, I had 11 functions and 4 variables in 4 dimensions. This is really hard to do. But the great thing is, when I'm SU2 invariant, I can necessarily write them diagonally. So that means the metric only has 3 functions, and then a 4th function with the soliton potential. So I have 4 functions and 1 variable. Great. This has reduced us a lot, and now we can hopefully understand these things. So here's my 4 equations, and 4 functions, a second order ODE. This thing still isn't very easy to do. It's quite hard to understand what these things are doing, but if we also assume we have more invariants, so a larger symmetry group, I can continue to reduce this. So for the SO3, SO2 invariant case, the ODE looks very similar, but a little bit different. And then I only have 2 functions. As with the U2 invariant case, these 2 of these 3 functions are the same, and I get 2 functions. And if I keep going and I have SO4 invariants, actually all 3 of these functions are the same. So I can keep reducing this by applying more symmetries. Okay, well, these are still just ODEs. You would expect these to be understood, but what is really difficult for this is the smoothness conditions. So let's start with a simple example. If I have a metric on R2, it's invariant under rotation, well, then writing it in polar coordinates is kind of the correct thing to do. We write it like this. If my function away from the origin is smooth, great. I've got a smooth metric everywhere apart from at the origin. How do I ensure it's smooth at the origin as well? Well, we can do some computations and see that this will extend to a smooth metric at the origin if and only if the derivative at 0 is 1 and all the even derivatives are 0. In particular, yes, I have an ODE, pick a point, solve the ODE, but that doesn't necessarily mean I get a smooth metric everywhere. I could get some kind of point here. Whereas if I ensure I actually satisfy these smoothness conditions, I know at the end, yes, I get a smooth metric. I also make a remark here that I can do orbifold closing conditions too to get an orbifold metric. And these are more generic than smooth, and we might find an example of those things later, and that might actually help us understand what the smooth examples are. Okay, so for our case, looking at the compact case, we have smoothness conditions at two ends. Our orbit space is an interval. So I have a smoothness condition at 0 and at some maximal value, say R. And the smoothness conditions, after reparameterizing correctly, necessarily look like either very similar to the polar action. So my function has its first derivative is 1 and all the even derivatives are 0. Or it looks like this kind of weird thing. And this is where not all the functions vanish, just one of them does. And that leaves me with a singular orbit that's CP1, maybe quotient out by something. Or just CP1, sorry. In particular, what we note here is that, well, the smoothness condition gives us, some 4 on n, and looking at the slice isotropy representation, we actually see that, if n is not 1, 2, or 4 in this case, I'm necessarily having f2 and f3 as the same, so I am U2 invariant. So that's why we could see before, from that infinite family, there was only 3 actions which were somehow minimal. Okay, and the space this is working on, like this is a fixed point action on R4, this is kind of some obvious action of SU2 on a twisted line bundle with twisting number -n over CP1. Okay, and it turns out, no matter what, at one end I look like this, and at the other end I look like this as well, but I might change my smoothness conditions a little bit, and that change depends on the action, of course. Okay, it is actually a little bit more tricky than that. For some, specifically 2 examples, I can't necessarily say what the smoothness conditions at one end and the other end are before restricting to my case a little bit, but this is a problem that can be resolved. There's a little bit more to do, but it's not too much. The other thing to note is that, well, because my isometry group is not abelian, I necessarily know that my compact 4-dimensional cohomogeneity one simply connected gradient Ricci solitons are actually shrinking. This should be lambda greater than 0, sorry. Okay, last thing to note is that if I have this Cassie term, and I write it like this, it's actually necessarily monotone increasing, and it can tell me where the singular orbits are. In particular, as I go to one singular orbit, the left one, then this C value goes to -infinity, and to the right one, it goes to infinity. And this is somehow a really nice way to parameterize the orbit space. Not only that, but for numerics, it tells us where the other singular orbit is. So let's do a numerical procedure. So what do? Looking at one singular orbit, I can approximate initial conditions near there using the smoothness conditions. So I approximate f, these functions and their low derivatives at some small value. Okay, now I just have an ODE, great. I can solve that to the other singular orbit, finding where the other singular orbit is via this Cassie function, so when that's very large. And then when that value is really large, I'm close to the other singular orbit. Now I compare to the smoothness conditions given by Verdani and Ziller, and I say some function SOL depending on what I got from my functions near there, and I can determine if that object is close to a smooth metric. In particular, I would say this SOL function evaluated on parameters that give me a smooth metric should go to 0. So if I'm a lot bigger than 0, I'm probably not smooth. Okay, well, let's apply this to some of our candidates. In particular, let's see what happens nearby metrics that are known to us. So I know I have the standard metric on S2. Apply this to metrics nearby. Let's see if we can find anything more. So here I'm plotting the sol function, and I'm doing the logarithm of that. So if I'm smooth, I should have my evaluation near -infinity. So I should approach -infinity if I had no numerical error. Now, what you'll note is that, yes, all the examples we can see, we can find, And around them, of course, this solve function should hopefully be continuous to actually distinguish these metrics. But when we start going further away, we're seeing that there's not really other candidates for smooth metrics. So we can play the same game on different actions. Here we see, this space, which was CP2, connect some with the reverse orientation CP2, and I get all the solitons I want, the coheso-South soliton and the page metric. Again, noting that there's not too much when we start going far away from these solitons. We can see the other examples. We have the round metric. Again, like we would expect, the round metric is kind of alone. And then we have the Fabini-Studi metric, which is this kind of intersection between the Kähler and Einstein metrics. So you can see it actually does make quite a big impact here. But again, when we start going far away from the Fabini-Studi metric, there's not really too many other candidates. Okay, along Kähler and Einstein here, there might be some, but we can analyze them more closely to see, well, in those cases, there's none. Okay, so how do we do that? First of all, let's have a look at the U2 invariant shrinking gradient Kähler Ricci solitons. Well, why would we do that? Looking at those pictures before, you can see that along the Kähler parameters is where we find almost always the things that are closest to closing up smoothly. So if I'm not Einstein, the best things look like they're the U2 invariant shrinking gradient Kähler Ricci solitons. So let's classify these things. In particular, quite often these things will give you orbifold singularities. And as long as the U2, the action, so let's suppose they have a U2 action. If that U2 action came from an SU2 action, I can actually list out everything these things could be. So necessarily assuming that we're over a simply connected full manifold, because otherwise this isn't too relevant to us. I have a shrinking Gaussian soliton, not compact. Let's not worry about that too much. And I have something else over this twisted line bundle. Let's not worry about that too much. These last two cases are what's important to us. In particular, I can get something with arbitrary cone angle on CP2. The one with cone angle 2 pi is the smooth one. That's the Fabini-Studi metric. And then I can, especially in this last case, get some cone angles on two sides, and this inequality in the left here, where I have 2 pi on Q1 is less than 4 pi on n, tells us that, well, if n is 1, I can get a smooth metric, and if n is 2, I can get really close to a smooth metric. In particular, I can have a cone angle approaching 2 pi, but not actually achieving 2 pi. Okay, so now, once we've done sufficient analysis of a singular orbit, understanding what these initial conditions are, we can say that the not necessarily complete gradient shrinking Ricci solitons, what they look like, that's a 3-parameter space. And over that 3-parameter space, we'll minimize over a 2-dimensional slice and see what that minimum value is. So where I have 0, these correspond to the Einstein ones. And then I'm going to plot what the minimum solve value was. Okay. So we see when it's 0, yes, I get all those Einstein examples back. Great. Now, again, I see my coheso-South soliton in green here. And then in blue, I have this weird thing on the side. So maybe I have a gradient shrinking Ricci soliton, a new one here. Well, as we saw with our U2 invariant things, this is just an artifact from this almost smooth, or the family of metrics that approach a smooth thing, but the smooth one doesn't exist here, unfortunately. Now, apart from that, we can see that this solve function evaluates very highly. So we should not expect to find a gradient shrinking Ricci soliton here. In particular, it's telling us that, well, after we've looked at these heat maps of the Einstein case, well, there's actually nothing more that the cohomogeneity 1 setting should be able to give us. So in lieu of some analytical uniqueness results, the cohomogeneity 1 simply connected compact shrinkers hopefully is a shut case. We shouldn't really investigate these things for new ones. Investigating them for uniqueness is a nice idea, but just from the perspective of trying to find new examples, cohomogeneity 1 is not really the way to go. And seeing the examples from before, really the next obvious action is toric. Okay, simply connected, we're not quite done yet. There is still some more things we can do. In particular, let's stop looking at shrinkers and let's start looking at expanders. Now, why would we do that? Well, the other thing that happens in dimension 4, rather than these, starting to get non-trivial, in some very loose sense, gradient Ricci solitons, I also can get some Ricci flat cones as my singularity models, or singularities that give me Ricci flat cones. And now note that we can also get a singular set of codimension 4, so I can get orbifold points in my singularity models. Apart from Ricci flat cones, we're not worried too much about that. We're just going to focus on the Ricci flat cones. And the reason why expanders are important here is, well, if I evolve to get a Ricci flat cone, what I can actually do is put an asymptotically conical expanding gradient Ricci soliton in. And, well, like we saw with the shrinkers, they get a singularity, a blow-up of curvature. So they concentrate curvature. But the great thing about expanders is they diffuse curvature out. So if I have this real big problem, and then I try to resolve the Ricci flow by putting in expander, I actually diffuse out the curvature that blew up, and I actually can continue this thing. In particular, the first example of flow through a conical singularity is given by this cohomogeneity one shrinker I showed earlier. We do that, and then the problem we get is I get a Kähler cone with a singularity at 0. Well, I can actually, there's an expander known that I can chuck in and keep evolving the flow. And apart from one point in one time slice, this is a perfectly good solution to the Ricci flow. This is essentially the next best thing. So ideally, if I have Ricci flow and it's going to give me a Ricci flat cone at some point, what I want to do is shove in these expanding solitons, and then I can continue the flow. And I really am still able to do the same thing. Of course, understanding topologically what happens is another question, because I can lose the topology here. I went from a twisted line bundle to just C2, but still being able to flow past this with Ricci flow is an important thing we want to do in geometric analysis. Okay, so that leaves us with the question, can I always do this? If I have a 4-dimensional Riemannian cone, does there exist a complete gradient Ricci, expanding Ricci solitons that's asymptotic to this cone? And, well, if my cone is over S3 or some finite quotient of this, well, the good news is yes, I can. So this is work done by Baumler and Chen in 2023. There always exist these things, but first of all, if I was a quotient of S3, then this does have isolated singularities. So this isn't the best example of a continuation of the flow. Ideally, I would just want a singularity at one point in one time slice, whereas here I have one point in all positive or all non-negative time slices. So not ideal in that scenario. And the second thing here is that this is not constructive. So coming at it from the cohomogeneity one perspective, I want to put my hands on these things. I want to feel what they're doing. I want to explicitly have examples and put them in. And so that leaves us with the question of, okay, can I do this in the cohomogeneity one case? Can I find some examples and see what they are? So the first thing we need to do, like the case where I had non-compact Riemannian manifolds and understanding what the actions on them were, well, on the compact case, let's understand what actions can I have on the non-compact case. So if I start with a simply connected non-compact Riemannian manifold, and let's say it's invariant under a cohomogeneity one action, then it's necessarily invariant under one of these, or equivariantly diffeomorphic to being invariant under one of these. Now, this first case, I have the action which is homogeneous on the first component, and I have a real line factor. In particular, this guy's not connected at infinity. So it looks like a cylinder. And if I want to glue this in, so starting at a flow, Ricci flow on a compact manifold, if I get a Ricci flat cone and I want to glue this guy in, my end result is not going to be something that's simply connected. Oh, sorry, compact. And well, that's not something I want to do. So we're going to ignore this case. It's still an interesting question of, what are the expanding gradient Ricci solitons in this guy? But from the perspective of finding an asymptotically conical one that I can continue the Ricci flow with, that's not too viable for us. Okay, so that leaves us with these two cases, or these three cases. So the first one, again, I have an SO3, SO2 action. This is a little bit more simple, and in fact, it's been resolved. I can say exactly what the expanding asymptotically conical gradient Ricci solitons on this guy is, and that's actually been finished in almost 20 years ago, and we've seen a similar case with an action on R3, S1, which has been resolved recently. We'll see that on the next slide. So it leaves us with these final two actions. I either have the standard action of SU2 on C2, or I have the standard action of SU2 on this twisted line bundle, like I said before. Of course, when n is 1, 2, 4, as we've seen, I get an action of SU2. And if n is not in those values, well, I can actually bump up my symmetry to assume it's U2 without losing anything. Okay. So what are the examples of these things? First, I have my one parameter families. Well, first I have my two parameter families that came from my SO3, SO2 things. This is everything. This is all we can get. There are some Einstein examples within here, but the majority are not. Okay, now let's look at the ones we care about. If I have U2 and SU2 invariants or more, well, what examples can I find? And these are all one parameter families. And in particular, what you'll note here is that to find these examples, I need to make the soliton equation quite tractable. In particular, either doing that by bumping up the symmetry. So SO4 here. So I only had one function and then, well, two functions. One is my soliton potential, and my metric is just reduced to one scalar function. Or I can say, let's keep with SU2, but now let's assume it's Einstein and Kähler. So getting a lot of different restrictions on there, that gives us a tractable enough equation to find another one parameter family. Or we can do something kind of in the middle. I can say, let's bump up the isometry just a little bit. So now I have U2 invariants somewhere in between SU2 and SO4. But to actually find some examples, we either need to assume it's Einstein or Kähler. And that gives us, again, one parameter families. These guys have all been found. In particular, there's also some ends to these guys, which gives us a discrete family, but these are the one parameter families that have been found. The question is, well, can I find anything more? So are there any SU2 invariant, but not more, examples of these complete, expanding, asymptotically conical gradient Ricci solitons? In particular, are there any that are not Einstein or not Kähler? And the answer is yes. In that three parameter family of not necessarily complete ones, starting from some initial condition, we can actually see that being asymptotically conical and complete is an open condition. So that allows us to find three parameter families of pairwise non-homothetic, complete SU2 invariant expanding gradient Ricci solitons on C2 and these three twisted line bundles. Moreover, these families each contain a two parameter family of Einstein metrics on their boundary. All the non-Einstein solutions, solitons, are asymptotically conical. Perfect, that's what we wanted. And we can also play this game for the U2 invariant ones. So if I have this twisted line bundle with twisted number not -1, -2, or -4, I can play this game again. Now I've bumped off a parameter. So now there are two parameter families. And again, I do the same thing, great. And there's a one parameter family of Einstein metrics along their boundary. These one parameter families have been found. There's nothing new there, but there is still a little bit new for all the solitons. Let's see how much bigger this space is, particular looking on the expanding gradient Ricci solitons on R4. So just look at the U2 invariant slice. We can see, these examples that have been found. So Einstein along the vertical boundary. We see Bamler's along in yellow here. And then we have in orange, the ones found by Sal. And then we have some individual metrics here. Well, it turns out that's definitely not everything. And what we found is in blue here. So we can find a lot more. And this is just the U2 invariant slice. We can keep bumping this up and get another parameter. So there's another dimension of these things we can look at. Okay, so that gives us some look at some shrinkers and some expanders. Well, there is another case here that we're kind of missing out, and that's the translators. So what about the steady case? Okay, type 2 singularities is where we're looking at the steady case, and this gives us non-collapse, well, ideally, we're looking for non-collapse steady Ricci solitons. These are the singularity models we want. And again, the cohomogeneity one setting is the maximal case of symmetry that we want to understand, but these are well known. In particular, we kind of can dimension reduce, and this problem becomes a little bit more simple, and a lot of examples are known. In particular, we have, this SO3, SO2 case is done again, and we have a lot of examples, and in particular, Appleton gave us some non-collapsed steady solitons. And for that case where the twisting number is -4, you can do this same procedure and get the SU2 invariant steady solitons on O4, the twisting line bundle with twisting number -4. And that again gives us, well, now it gives us a 1-parameter family of these guys. So hopefully that's given you an overview of the cohomogeneity 1 case for gradient Ricci solitons in dimension 4, in particular when their symmetry is somehow minimal in the compact case. That's all I had to talk about today.
Thank you very much, Patrick, for going through all of these Ricci solitons for us. Does anyone have any questions for Patrick regarding the work that he's described here, or anything that is related? I suppose I have a question for you, Patrick. So I guess expanders and steadies are necessarily non-compact,
Yes.
but shrinkers are not necessarily compact.
Yes.
Have you done much in the way of studies of non-compact shrinkers? I mean, of course, there are some that are known, like the FIK shrinker.
Yeah, so there's the two we had here, all the way back. There's the two known ones that are kind of non-trivial, so the FIK and the BCCD.
Yeah.
So the FIK one is the kind of one we want to model. In particular, when we were looking at the orbifolds, we can find a family of these things, which include the FIK soliton. And I mean, you can try and play a similar game where you look at, do numerics and see if you can find anything new. But where we were more focused on the compact case, that's a little bit more interesting to us right now. But again, if you do that, we'd expect that, again, cohomogeneity 1 is kind of too much. Everything's been done there. You wouldn't really expect to find much new in that way.
So even with the weaker SU2 invariants, you wouldn't expect to see anything new.
Yeah, again, similar to the compact case, you wouldn't expect much. But of course, this hasn't been investigated too much. Of course, there's still potential for this.
So if you constructed some orbifolds, does that include non-compact orbifolds?
Yes, yeah. So the first two examples here, so you can actually do this to get a lot more orbifolds that aren't over a simply connected 4-manifold. But these, if I include all my examples where Q is not necessarily an integer here, these are actually just trivial quotients of the stuff I've found here.
Okay.
So really the only non-trivial, non-compact ones are these ones on the twisting line bundle. And that gives me a smooth example exactly when n is 1. Because again,
Okay.
I can do the same thing. And like we saw in the compact case, and we had this family which is almost smooth. If n is 2, again, I can do this family of almost smooth metrics, but they're not exactly smooth. Or
Okay.
it's not one that's smooth.
Great. Thanks for that. Does anyone have any other or further questions for Patrick about his work or related topics? Great, then I suppose we'll leave it there. Let's thank Patrick again for taking us through his research. Awesome. Thanks all for joining us. It's likely that we will have a talk next Monday as well. We'll send details about this in due course. Thanks again for joining, everyone. I'll stop recording there.